Hello everyone. Today I'm going to explain about advanced database model. Last week we looked at the file database systems, and for short period of time before we get relational database, we have a hierarchical and network databases. Mid 1970s and early 1980s, we have a relational databases that has been popular and so far widely used, and the technology and theory behind have been evolved and advanced very much. And then in the late 1980s, the database community tried to think how to improve the semantics in the database. How can we include the meaning of the real world structures in the database? Relational database, as you might know, is very simple, but it provides a strong declarative language, which is SQL. SQL is a declarative language, which means that is not procedural language. So that is declarative. That is non-procedural language, which is good. But only the little bit drawback of relational database is that it doesn't contain the deep level of the semantics. And around that time, the programming language community has developed the new paradigm. We call it object orientation paradigm, object-oriented paradigm. What that paradigm initiated was everything should be considered as objects. So objects may be grouped together, will become a type, or we call it class. So we need to structure the class and the relationship among those classes. That has been well implemented in the programming languages. First well accepted programming languages for object orientation is Java programming language. And since then, almost all the currently used programming languages include object-oriented paradigm. Some languages started with object orientation. Some languages we don't simply ignore object-oriented paradigm, but we can still start, and in the meantime we can include object-oriented features, which is like Python. All right, so object-oriented database is very hot in late 1980s and 1990s, throughout all 1990s. The features that we can think of object orientation paradigm from the language also available in databases. So object is it has two features: structural aspects and semantic aspects, okay, or behavioral aspects. Those should be implemented in object-oriented models. Table which says here factual content and also relationship between the facts. This is structural facts, and then relationships among those. So object becomes basic building blocks for autonomous structure. So it can increase or decrease. The features can be increased or decreased. It could be very complex data models. That is also possible. Like we looked at entity relationship diagrams. That diagrams can be seamlessly implemented in object-oriented databases, which was not the case for relational databases, right? In the relational database, we have to simplify it. We call that design the logical design. So all entities will become or converted to a relations or a table in relational database. But diamond, the relationship in entity relationships, diamond will become either a separate table or the fact associated with that diamond will appear in one of the participant entities. That participant entities, the attribute migrated to that participant entities is called foreign keys. Not all of those, but foreign keys comes from there. Those things can be very nicely implemented in object-oriented databases. So what was that in a minute? So object-oriented data model became possible to support increasingly sophisticated transactions information requirements. Sophisticated transactions, which means in relational database, if you want to map with the relationships, relations tables in a little longer distance, then you need to make a multiple joins. Object-oriented databases, you simply traverse. You can propagate from one class to another class and another class. You can jump. Okay, that is possible. So very sophisticated transactions possible. So with that in mind, basic structures of object-oriented database is composed with objects. And objects is constructed over attributes. Some of the attributes, the type of some of the attributes simply an atomic type, atom, just a value. Some of the attributes type may be yet another class, like object-oriented programming, right? Type of an object will be another class. Objects that share similar characteristics are grouped in a class. Okay, but in real implementation in object-oriented data model is not starting from object, like in programming. We start from class. Because object-oriented database follows rigid the descriptions or definition of database. Okay, so we first define a class or a table. Based upon class or table, we can populate data. We don't populate data first and then group them. Okay, we can think that way, but in real implementation, it should be top-down approach, not the bottom-up approach. So define class, and then define class hierarchies. Along these hierarchies, along the classes, then we can define objects. Okay, objects. Of course, when we define class, then class is defined over attributes. Okay, attributes can be defined in a class. Type of object then will be another class or will be an atomic value. So with that, if it is a type, if a class is a type of another attribute, that is the point one class can connect to other class. Inheritance is also possible because that is hierarchical. Everything that you defined in the upper class or superclass can be inherited by its subclasses. For example, let's say superclass is student, okay? Superclass is a student. That superclass has subclasses. Could be, when we looked at objects, part of those objects are maybe undergraduate students, part of those objects are graduate students. Then we can say we have two subclasses under the class called student. Okay, so pictorially we can say that in this way. So this is a student. Student has undergraduate students. Student has a graduate. Students is again the subclass of, in general, people. There will be another subclass, not necessarily student, but maybe faculty. So we have hierarchies. Top, we have person. Subclass of person is student. Another subclass of person is faculty in the college database. And then part of the subclass of students will be undergraduate students. Part of the subclass of students will be a graduate students. Hierarchically, we can design in this way. And then there is an inheritance. We can define, as we define this class, person, we define with, for example, last name and first name, okay? And then undergraduates, the students, which is a subclass 2 person, we can now define here, we don't need to define last name and first name. If I am students, because a student is a person, students can have all the properties associated with the person, because a student is a person. So without having to define last name and first name, student also has a last name and first name. Faculty here also student faculty has a first name and last name. In addition to those inherited from the superclass, is inheritance. And then the student has, for example, major, right? And student has a GPA. In addition to the last name and first name, which are inherited from the superclass, faculty might have, let's say, rank. Faculty has salary, for example. Similarly, student has a subclass undergrad, and then subclass graduate students. For undergrad, we don't need to define again last name and first name. We don't need to define major and GPA. So both undergraduate and graduate students has this last name, first name, major, and GPA. In addition to that, undergraduate might have some others. Okay, maybe capstone project. Graduate students might have a thesis topic. Okay, so this class has only thesis topic, but because these graduate students can inherit all the properties from the superclass, but because the student is a superclass 2 grad, and also person is a superclass 2 students, which in turn 2 graduate. So graduate class can inherit everything that's available on person, that's available on students. So everything that are inherited together with the newly defined in the class, that'll be the property of this leaf node classes. So very, very efficient. In this way, in the earlier slide, there is a code reusabilities. Anything that we could write here, the code, something about last name and first name. Not only these structural data are inherited, but behavioral data, some functions defined in person can be inherited by all of these subclasses. Function defined in the level of students can be available by graduate students and undergraduate students. So both structural and then behavioral, both attributes and functions or methods can be inherited. That is code reusabilities, right? So a lot of good features available in object-oriented databases. So if we compare entity relationship diagram to object-oriented databases, that is in this way. This is an ER diagram, right? Entity relationship diagram. We already know. And if we try to use some arrows, then we can put arrows like this, right? So students can should measure only one department. Department may have many students. Department may have many faculties. Each faculty should be affiliated with one and only one department. Faculty can teach multiple classes. A class can be taught by one faculty. A class can allow many students to be enrolled. And A students can enroll in many classes. So those are all the inherent semantics. Those can be implemented in object-oriented databases. It looks like very similar to the relational schema in relational databases. The schema can be schema will be a set of attributes or set of attribute and type pairs. Here students has a CWID, that is integer, name, text, major, in this case, department. If it is a relational database, we say that major is text. But in object-oriented databases, the type of a major is a department. What is a department? Department is another class, another table. In object-oriented database, that is the classes. I mean the table is nothing but a class. The class can be defined. Students is a table, but the value to the attributes is not atomic data, but this is another class, another specific class member. We call that objects. So there is object ID. See here, OID. Object identifier is generated for each record. So major, for example, if some specific person, name John, major, if it's a cyber security, then cyber security has also a specific object identifier. That OID comes here. Okay, that object ID. So since John is definitely linked with the department cybersecurity. In the class of department, in the table of the department, there are two attributes: name, department name, and chair. Name in text, chair in faculty. Okay. So again, faculty is not the atomic type, but faculty is object ID. Faculty here is a class, therefore, if it is a specific faculty ID, that faculty ID plugged in here, chair. Okay, so faculty class or faculty table has attributes name and affiliation. The affiliation of a faculty is a department, right? So again, the type of the affiliation to faculty is the OID of a department. If that faculty is affiliated with the cyber department, then cyber OID will be the value to this affiliation. Another faculty, let's say Peter, okay? Peter affiliations is Department of English. Then English OID will be the value to this Peter's affiliation. We have a class title, and the class has instructors. So instructor, the type to the instructor is not just a text, so that we can put there John. We don't do that here in object orientation, but faculty object ID. Okay, rather than we say John, we can say what is John's ID? John's ID will be the value to this instructor. So by accessing this class, if you want to know, oh, I want to see faculty, I want to see the faculty's affiliations. I want to see the faculty's affiliations, department chair affiliations, a supervisor, for example. Who is the supervisor of the department where a particular class instructor is affiliated? Very complicated semantics, right? That is very nicely traced here. If I see here a particular type class, okay. Let me point option pen. I did that already. Okay, a different color. Okay, so for this particular case, is hey, this particular title, I want to see instructor's affiliation. Then there is an OID of that particular class, right? Because this is a particular, that. So from this OID, then I can simply know which faculty. Because I know that faculty, I have departmental OID, right? Once I know departmental OID, come back here. I know department chair. So I can say, hey, Smith is the department chair of the department that your instructor is affiliated. If it is not the case, if it is not object-oriented case, what should we do for the same query? Then we need to do here. Then we need to multiple joins. I need to join class, because class has, if we know class has instructor, so instructor is nothing but faculty ID. So in select from close, select, let's say star. We want to select everything. From, I want to select class, comma, faculty. So class and faculty are joined together. If we join, then there should be join operation. Where? How can they be joined? They need to be joined based upon faculty ID in faculty and instructor in class. So what I need to do is FID, faculty ID should be the same as instructor. And then we still go further. This faculty's affiliation should be the department ID, the same as department ID. And then we need to see the name, department chair's name. So we need to have another join, another table to join, which is department. So we have a department here. So we have three tables are joined. First two tables are joined based upon this join operation. And then we need to have another join operation by connecting with the AND operator. Affiliation should be affiliation in faculty, so that we have affiliation. Affiliation should be the same as department DID, D_ID, D_ID. That should be the same. So class is joined with the faculty, and the faculty is joined with the department. Join conditions are not the same, right? The first join will be based upon faculty ID. Second join will be based upon the affiliation here and department ID there. And then we can finally select name. If we don't want to extract all the attributes for specific attribute, then we need to specify here name. Then that will be the department name. If there is a ambiguity, the name by name only, because we have a department name and that name, so it should be chair, right? Chair's name, right? If there is any ambiguity, if we need to describe something, the name of the department, the name of the faculty, and then name of the students, strictly, explicitly differentiate, then we use dot operator. Not just simply name, but we can say student dot name. Dot name. Same thing, not just the name, but if it is about the faculty, then we need to say faculty dot name. Dot name. Similarly, our department name, then we need the department. Dot name. All right. So this is a SQL statements. Select from where we have a multiple tables, and then where we have multiple join conditions specified. That could be in object orientation in a very simple way. We can say okay, faculty here. So particular title, say IASP .525. This is a particular objects, okay? Objects, a faculty, an instructor. Object dot, so this is an object. Object ID. This is an attributes. So this object has an attribute instructor. That instructor, whatever that OID is, because that is nothing but faculty, so we simply say faculty's, this instructor's affiliation. Instructor's affiliation. Instructor, it's kind of, it's not really inheritance, but kind of. This is a semantical relations. So instructor is a faculty, so faculty has affiliation. Let me put it in this way. The instructor of a class is a faculty, and the faculty has affiliation. Therefore, class instructor has affiliation features, affiliation values, right? So that we have an affiliation here. But type of affiliation is the departmental OID, right? Faculty's affiliation, since the faculty's affiliation is department, the department has the chair information. Faculty has his or her own chair information because, I mean, through affiliation. So we put here, we have affiliation here. Through affiliation, we know chair. Okay. So we have 3 dots are used. 3 dots are used. Those dot operation nicely will be the functioning like we do have a join operation, right? We have 3 dots. This OID has instructor objects. Instructor has affiliation objects. Affiliation has chair object. Therefore, this one expression tells you the chair of the department where that particular class instructor is affiliated. I think you can see some of that implication here, right? But it should be connected with the dot notation step by step, as you can see here. Think about this and there here. What's the difference, right? This is SQL. This SQL is looks like this is more complicated. Well, it has more, more text, more characters, right? But this SQL statements is maybe better for the database engine to understand. If we see here object-oriented path expression, this path expression, then this path expression is not easy and simple to implement in object-oriented databases. That is the thing that we need to consider. Okay. So this is the comparison between relational database and object-oriented databases. The structure or definition of class or definition of tables look similar, right? In this relational database, all the data that inserted into the attribute should be primitive data. Okay, they're all text, integer, those things. This is RDB. But object-oriented databases, the data that can be inserted into each attribute could be primitive or could be yet another object ID of the class, of the table. Okay. See here, department, and then there's a department. It's not like here. Okay. This is RDB, this is object-oriented. If you understand this slide completely, then I would say you understand the difference between relational database and object-oriented databases. Okay, this object-oriented database is fully implemented in OR database, object relational databases. If you use the advanced features of current commercial DBMS, like Oracle, then Oracle supports OODB like this. You can implement, you can define tables, you can define tables like this in Oracle, or you can still define table like this in Oracle. Relational database or object-oriented database, both are accepted. But the using is not the same, right? As you imagine. In addition to this structured, well-structured DBMS, recent years, we also think of unstructured databases. Since late 1990s and early 2000, the database communities started thinking of XML databases, extensible markup language. XML is very similar to HTML, but HTML is a strict subset of XML. XML is much more flexible, but because it is flexible, and also because HTML is a strict subset, and it is based upon some of the data type, and also it is good for visualization. So HTML delivers you how to display on the terminal. That is what HTML is. That is what web page can do currently, right? So HTML. XML is much advanced than HTML. And originally, the superclass of both HTML and XML is GML. GML was defined 1960s, 1950s, 1960s. But it was not, it was thoroughly used in a small community, which is digital libraries at that time. Not widely used, definitely not to computer communities, computer science communities. In late 1990s and early 2000s, because this is non-structured data became popular. Why it became popular? Because there is HTML documents populated over the internet. Therefore, database community think of, oh, we need to develop, our database system should be evolved to adapt unstructured data models. Okay, so that is XML. XML is the first generation of unstructured databases. So a lot of papers had been published. I published also about maybe 20 technical papers. Some of them in journals, some of them in conference at that time, early 2000. And I implemented that XML databases, partly using Oracle, partly using Java. It's very nice. We can accommodate any XML data, which is a superset of HTML. And also we can define how to visualize HTML documents and also how to relate with the other XML documents. So relationships exist and data exist, and also visualizations available. That is what XML can do. But XML itself is just documents. It needs a lot of the coding behind the Java coding. And early 2010, database community started thinking of NoSQL, okay? And meantime, in computer programming community, they developed a well-structured data type, which is a JSON. Okay. Those who learn Python, then Python provides 3 basic data types, which are list, tuple, and dictionary. Okay, so both list and dictionary together, we can confirm JSON. So JSON data formats does not rely on any predefined data definition. It's simply stated, okay? And therefore, without having to have the conventional SQL statements, we can still access data in the database. We can still access collections in, for example, Mongo database. Okay. So NoSQL is also possible. If we compare relational database with NoSQL, simply in this way, in relational database, then faculty ID, name, and affiliations, and then this is a faculty table, and this is a publication table. John in cyber, who wrote two textbooks, Java in 2015 and Python 2020, right? We could have more and more. So one faculty might have a multiple, one faculty here, one row in this table might have a multiple rows in another table which are connected, right? John here can be mapped with 4 or more records in another table. That is possible. Because this guy has 4 or more or many, we cannot define these two information in one table. Okay? We don't do that in one table. Why? Because there's some anomalies expected. We can explain that in the normalization process. If we combine these two tables together, these two tables are very simple and defined in simple way, and they can be combined at any time if we need by joining operation, right? We can join faculty and publication. Then we can access the values at any time. But in structure-wise, we don't combine them in one table. Let's say faculty has 4 records. By having here, this will be continuation of this table definition, then this goes together, right? This is something about title, and this is something about year. This is something about author. Author is named here, so we don't need to. Actually, this is a join operation, right? When we need to join, this is join operation. We could have these 2 attributes, but we may have 4 records. In that way, we can include the 4 of the publications come here. 4 books comes here attached. So we have 4 different book information here. However, we have to repeat these 3 as many times as this guy is available. If this guy has 100 books published, then the first 3 attributes repeated 100 times. The very same value should be appear 100 times. What is the drawback? What is the problem? Is there a problem? Someone may say, oh, it's not a problem, only the efficiency issues or storage abused. We need more space to make the repetitions. That may be true, but it might have a more severe problem. Might have more severe problems. In this particular case, for example, John's affiliation is switched to another, not cyber, but maybe artificial intelligence department. John affiliated with artificial intelligence. If we have 100 times of cyber, then we need to update it 100 times. Let's compare that situation with these 2 tables separately. 2 tables separately, then we can only update here. That affects 100 times whenever we join them together. Not necessarily physically repeated 100 times. Big difference, right? But anyway, this is a very nice relational database design. So we have 2 tables, faculty and publications. That could be available in not having to that anomalies by combining those 2 tables physically in one. But we can have those here. This is JSON formats. Okay. So we have a list. Okay. And then in curly brace is dictionary. Dictionary is a collection of key and value pair. This is key, colon, value, comma, key, colon, value, comma, key, colon, value, comma, key, colon, value. Book is, or publication, is a key, or we call that attributes, has a value. Value itself is not atomic value, as we could see the other case. Affiliated, the value to affiliated attribute could be cyber, but value to the attributes book will be another list. See here, list starts, this is end. Book is a list of dictionary. First dictionary in that list is from here, there. Second dictionary in that list is from here and there. So first dictionary, title Java, year 2015. There's a first element in an array. If we want to here, if you know the concept of array is nothing but a list in Python. So first element in the list, or first element in an array, that is the first book here, Java. Second element, which is the second curly brace, title and year pairs, that is the second here. It could be multiple, it could be no nothing, right? There are many multiple different ways. If we want to rewrite it in pretty printing methods, it could be like this. This is exactly the same one that we looked at. Faculty ID 1212, name John, affiliated cyber, book. This is the first book. This is the second book. Both are in curly braces and all together in this bracket, which is an array. So that is a value to the attribute value, attributes. Okay. So this is a JSON. NoSQL database system insert the value into a collection in this way. This is the value to a collection. If we enter this records, this JSON data, then it could be this whole in relational database, right? That will be a lot. Right. Everything here is everything here. But this is a JSON data. JSON data this is a document. This is not structured. Why? Because the value to book could be one only, single attribute. Then there's a structure. But in this case, it can be expanded further and further, depending upon the records. If it is John, then it could be 5 textbooks. If it is Peter, then 0 textbook. If it is David, maybe 1 textbook. Each one is different. It could be no values. It could be another complicated data. So all those situations, all those values can be possible in NoSQL databases. There's a reason that we say, oh, NoSQL Bongo database is so popular. It's popular. Not necessarily Bongo, but many other commercial DBMS also support NoSQL. NoSQL is one part of enterprise, big enterprise. Okay. The better DBMS supports better physical data model. If it supports better physical data models, then database can function efficiently well. Efficiently well means higher performance or accurate result. So we started with conceptual data models, conceptual database design. Now we are in the physical database design. Physical database design. So depending upon the physical database design, we can make our database more efficient. In this database design, it requires some of the data structures. If you do not have data structure concept from computer science, you might have some difficulties, but don't worry too much. If this is first time that you hear, then take it, okay? This is very superficial level of understanding, but I want you to see, hey, those the file organizations is a part of the technologies. This is very, very primitive. This is the first concept, but could be great in-depth advancement available, but you don't need to do at this point, okay? But eventually you may know. Let me go this quick so that you don't get much stress about this. But this is all very useful. We already know, we already developed tables, a number of tables. Each table has a number of rows. So those tables in a row or rows, how can they be organized? Sequentially? So if it's a table, let's say this is a disk, okay? Then first record here, second record there, and fourth record there, first come, first served, okay? And piled up. If this is deleted, then maybe this is empty. Later, if this is used, then another data can fit in, and this maybe further and further, right? Sequential. Indexed or hashed. Factors for selecting file organization comes from the need. Fast data retrieval, throughput. If you need fast data retrieval, then what data structures or what file organizations that you need to adapt. Efficient storages are going to concern storage only rather than retrieval. Okay, this is storage. This is a retrieval issue. Or protecting from failure if you have some security issues. So you want to keep it secretly, tightly from any failure. Or minimizing need of organization, accommodating growth, because data increases and decreases so fast. So that is your concern. Or data once stored, it'll go forever. So that you wanna, this is not the case. How can you, which data organizations that you want to use? So all depends. Security for unauthorized use. So this is a sequential data organizations. Okay, all the data sequentially. If it is a sequential, then access time is really bad, because every time you have to search from the top to bottom all the time. There's no quick access. But if you do in another way, for example, index file organizations, we call this B tree or B plus tree. Okay, this is B plus tree, right? This is tree structure. Tree structures. So as I said, this is a balanced data type. Let's say this is well structured. Whichever you go, which one you want to go here, how many nodes that you can access? 2. First you access here, and then you know that goes through this path, then you know where you need to go. Okay, so 1 and 2 and 3. If you don't go anywhere here, that is also the same thing. 1 here, 2 here, and 3. Anywhere here, 1 here, come back here, 2 and 3. Whichever your data is, the retrieval time always the same. That is B plus tree structures. Okay, if you want to make sure your system supports users' inquiry in the acceptable return time consistently, then B plus tree may be the issue, right? Maybe the solutions. Another one is hashing algorithms. Looking at the key, if you want to find out by major, then look at the major, then you know where you need to go immediately, because there is a hashing value. The way that you structure the data, the way that you can retrieve as well. You can see the address quickly from that computation. There's a hash algorithm. That is also possible. All right. So having those different data organizations join operations will be the killer of query optimization. It depends on the organizations, right? Or you can speed up the join operations if you want to. Therefore, if 2 tables are heavily joined by this type of this group of users, then when it comes to that the inquiries from that group, then you don't need to go each individual tables. You go to like already combined tables, joined tables. That way you can save the return time. Okay, so all the optimization issues. This table summarized that so sequential indexed and hashed. If you want to do random retrieval by primary key, then which one is the fast? Hashed is very fast. If you want to delete records, which one is fast? Very easy, and all depends, right? So you can see updating record. If you want to update, which one's better? Adding new records, so require the rewriting files in this sequential case. In indexed case, sometimes, yeah, it should be reallocated. The hashed structures, very easy to do new records, adding the new records. Sequential retrieval by primary keys. Of course, the sequential file organization will be the best. Okay. This is moderately fast indexed, the B+3, for example. Okay, database interface to users. There are many ways. This is what we could do the next week. We'll build MySQL. I wanted to install MySQL and get it ready so that we can do next week altogether. Command the line first. And then host applications. Which is one of the host languages is Python. So Python can embed SQL statements. So as we execute Python code, can access database and return. In this case, we have an app here and the database there. Directly connect. That is this host application. Web application is a little different. We have an app here, database there. There's a web server here. So we access the web server, and web server access MySQL. The other one is remote applications. So we have a database here. We have smartphone, for example. This smartphone has applications. If you click here to retrieve, then it goes to that database and come back. In this paradigm, you simply use Python. In this case, you simply hear Python at the application. But you need to have here, for example, web servers. It could be PHP or something else. Your smartphone apps, you could have, for example, Swift for iPhone or Java for Android. That Java or Swift directly go to, no, not necessarily. Usually it goes to PHP, and PHP access this. You can do this, but it is very dangerous, right? Database open to millions of smartphones directly. Then there's a security issues. So in between, you need to put web server, PHP. So PHP will be a cushion, will be a buffer between those two entities, sender and receiver, or request. I think this is something that we prepared before we do hands-on exercise with real MySQL databases. Okay, I hope you understand with this. And then when you come back, please come back with your MySQL database running environment. Thank you very much.